The future of AI is purpose-built systems. Executive summary: AI today largely runs on repurposed GPUs, but their limits in efficiency, latency, and energy use are driving a shift toward purpose-built systems. These integrate hardware, firmware, operating systems, and applications optimized specifically for AI workloads. Companies like Cerebras, Grok, Google, Meta, Microsoft, Amazon, and Huawei are leading with chips and ecosystems designed from the ground up. Purpose-built systems improve performance, reduce power consumption, and enable real-time or edge AI. While challenges include high design costs and potential ecosystem fragmentation, the long-term future of AI depends on vertically integrated stacks intentionally engineered for scale, speed, and sustainability. Article: For decades, the tech industry has often built amazing new things by repurposing old ones. The modern boom in artificial intelligence is a good example. Most large AI models today run on graphics processing units, GPUs, like those made by NVIDIA. GPUs were originally designed to draw images for video games and 3D graphics. Engineers discovered that the same math that makes realistic shadows and reflections is also great for training neural networks. That happy accident kicked off a revolution. But accidents don't last forever. As AI becomes more central to science, business, and daily life, using repurposed parts is starting to show limits. Training frontier models takes months and costs millions. Running them for everyday tasks, from search to chatbots to robotics, requires enormous energy. Latency, the delay between asking a question and getting an answer, matters for things like self-driving cars, medical imaging, and fraud detection. These demands are pushing us towards something new: purpose-built AI systems, where every layer, hardware, firmware, operating system, and applications is designed to work together for AI and nothing else. Why GPUs aren't enough? To be clear, GPUs have been a huge success for AI. They are flexible, programmable, and available at scale, but flexibility has a cost. A general-purpose chip wastes power and silicon area on features an AI workload might not use. Memory is a major bottleneck. Many models are too large to fit on a single GPU, so they must be split across many chips and moved back and forth over complex networks. That movement is slow and energy-hungry. Also, the software stack that grew up around GPUs wasn't designed for the exact needs of today's largest models. The result is progress that feels impressive, but also increasingly inefficient. What purpose-built really means. A purpose-built AI system is not just a faster chip. It's an entire stack that is co-designed so each layer reinforces the others. Hardware focuses on the kinds of math AI actually does, dense and sparse matrix operations, and on moving data with minimal waste. It also includes specialized memory and high-bandwidth interconnects, so chips can talk quickly. Firmware, the low-level code that runs on the device, manages power, scheduling, and data flow to keep the hardware busy instead of waiting on memory. Operating systems and compilers translate models into instructions the hardware can run efficiently, automatically optimizing for parallelism and locality. Applications are written with the whole system in mind, taking advantage of features like faster attention kernels, low-precision formats, or near-memory compute. When all of this is designed together, the system delivers better throughput, how much it can do per second, lower latency, and much higher energy efficiency. Leaders building the new stack. We can already see this shift in the market. Several companies are designing AI-specific chips and pairing them with software stacks tuned for their hardware. Cerebras builds wafer-scale processors. Instead of cutting a silicon wafer into many chips, they keep it as one giant chip with hundreds of thousands of cores. This design brings compute and memory close together and reduces the need to split models across many boards. Their software compiles models directly to this architecture, aiming for simple scaling and high utilization. Groq focuses on ultra-low latency inference. Its architecture streams data through a pipeline to minimize delays, which is valuable for real-time applications like conversational AI, trading, or robotics. Their compiler and runtime are designed to guarantee predictable timing, not just raw speed. Google has developed TPUs, tensor processing units, with custom interconnects and data centers built around them. Crucially, Google's software, TensorFlow, and XLA co-evolved with TPUs, allowing optimizations like low-precision formats, bfloat16, that maintain quality while cutting power use. Meta has announced its own in-house inference accelerators, MTIA, to serve massive recommendation and generative workloads. Meta's advantage is end-to-end control. It can tailor hardware to its models and vice versa, squeezing out efficiency at the scale of billions of users. Microsoft is building the Maya accelerator and optimizing the Azure cloud around it, alongside its Cobalt CPUs for AI-adjacent tasks. Because Microsoft runs huge AI services, it can design everything, from the chip to the rack layout to the cooling system, to suit model training and serving. Amazon AWS offers Trainium for training and Inferentia for inference. AWS integrates these chips into its cloud with SDKs like Neuron, giving developers higher performance per dollar without needing to be hardware experts. Huawei has its Ascend line of AI processors and a full software ecosystem. In regions where Huawei is a primary supplier, this stack provides a domestic alternative and pushes diversity in designs and standards. These aren't just chips, they are ecosystems, with compilers, libraries, model parallel tools, and data-centered networks engineered to fit together. The importance of memory and interconnect. AI speed is often limited by memory, not math. Large language models need to access billions of parameters and activations quickly. Purpose-built systems tackle this in two ways. 1. Closer, faster memory. Designs place large amounts of fast memory on the same package as the compute cores, like HBM, high bandwidth memory, or even on the same silicon. This reduces the distance data must travel. 2. Smarter networking. When models are split across many chips, the interconnect becomes critical. Custom fabrics and topologies like Taurus or Dragonfly networks reduce congestion and keep communication predictable. Purpose-built firmware schedules these transfers so chips don't sit idle. Together, these changes can yield big gains in throughput per watt, the most important metric when power and cooling are scarce. Software that knows the hardware. A specialized chip is only as good as the software that drives it. Purpose-built systems ship with compilers that understand model graphs and can automatically transform them, fusing operations, reordering computation to reuse data, and quantizing numbers to smaller formats without losing accuracy. They also include profilers that show developers where time and energy are spent, and libraries with tuned kernels for attention, convolution, and sampling. This is where purpose-built beats repurposed most clearly. Instead of trying to force a general tool chain to behave, the software is born for the hardware. That saves developer effort and multiplies performance gains. Edge AI and on-device intelligence. Not all AI runs in giant data centers. Phones, cars, cameras, and factory robots need fast, private, and reliable intelligence on the device itself. Purpose-built edge chips. Think of the neural engines in phones or the accelerators in driver assistance systems, fit tight power budgets, and offer hard real-time guarantees. They enable features like live translation, on-device photo editing, and safety-critical perception without sending data to the cloud. As models get better at running in smaller formats, the value of purpose-built edge hardware rises. Benefits beyond speed. Designing AI systems end-to-end has ripple effects. Energy efficiency. Data centers are hitting power limits. Purpose-built stacks extract more work from every watt, reducing cost and environmental impact. Predictability. Deterministic latency is crucial for interactive and safety-critical tasks. Security and privacy. Custom hardware can include secure enclaves and memory protections. On-device AI keeps sensitive data local. Cost control. Vertical integration lets companies avoid bidding wars for GPUs, plan capacity better, and offer more stable pricing to customers. Challenges and trade-offs. Going purpose-built isn't easy. Custom chips are expensive to design and take years to bring to market. Software ecosystems around new hardware can be immature, which frustrates developers. Standards may fragment, making it harder to move models between platforms. There's also a risk of lock-in if one vendor's stack becomes too different from the rest. These challenges can be managed. Open-source compilers, common model formats, and interoperable runtimes help portability. Cloud providers can offer multiple backends under the same API. And as more companies adopt purpose-built designs, the shared tooling will improve. Where this is going. The likely future is a hybrid landscape. GPUs will remain important, especially for research and flexible workloads. Purpose-built systems will handle the heaviest training runs, the most latency-sensitive services, and the most power-constrained devices. Over time, expect more vertical stacks where hardware, firmware, operating systems, and applications evolve together. Companies like Cerebras and Grok show what happens when you rethink the chip. Google, Meta, Microsoft, Amazon, and Huawei show what happens when you rethink the entire data center around AI. The core idea is simple. If AI is the workload that defines our era, then it deserves systems designed for it, not leftovers from another domain. Purpose-built stacks unlock better performance, lower cost, and new capabilities. They turn today's clever repurposing into tomorrow's intentional engineering, and that's how AI will truly scale.